Good afternoon, everyone. I'm Giovanni, and today I wanted to talk to you about this topic which I care a lot about, which is mitigating unwanted recommendation in recommendation systems. And as you may know, recommendation systems are known to contribute sometimes to the spread of potentially unwanted or harmful content in the recommendation. For example, recommending distressing videos to pregnant women, which was in the news not so long ago. And unfortunately, mitigation strategies that are employed suffer for things like low user awareness or limited effectiveness. And therefore, users tend to usually develop false theories to understand how to influence these kind of systems. So in this paper, we try to answer this question, easy question, about how can we mitigate exposure to unwanted content by using simple binary user feedback, for example, recommend or do not recommend a certain item. And we want to do it provably, which means with some theoretical guarantees about the effectiveness of this approach. So first of all, we started by analyzing a dataset from a very large video sharing platform. This dataset is peculiar because as far as we know, it is the only one that provides the explicit do not recommend signal that user can send through the application to say, I don't want to see this video in my feed. In our initial analysis, we tried to look at the behavior of users when they report a video. And just to be brief, we've basically found a couple of interesting facts. One is that despite the negative feedback on certain videos, there is the slight probability that the user will see those videos again in their feed. And also that very short engagement can be used as a proxy to determine if a video will be deemed unwanted by a certain user. And this is a factor we will exploit later on. So how do we, let's say, implement this kind of risk control within these recommendation systems? We started from this very simple two-stage pipeline in which we have our item pool, which is which contains items that the user might like or not like. Then we have a filtering step where we compute a certain score for each item to determine if they will be deemed unwanted by a certain user, and we just threshold them and we filter them out. And then we have the final re-ranking step in which we rank all the items and we report the top K items to all the users. As our risk function is simply this one here, which basically means is the fraction of the items that the user will report once he or she sees them in her feed. Therefore, basically the problem boils down to answer the following questions. We want to find the optimal threshold lambda that we can apply in the filtering step such that we can keep the risk, expected risk, under a certain given level alpha, which can be, for example, provided by the user. In order to do so, we employ a very simple but powerful technique which is called the conformal risk control, which enables us to provide the finite sample and distribution-free guarantees. It tells us basically that if we can exploit, for example, a calibration set, which is a data set with historical interaction pattern between user and items, and if we were to choose the lambda this way here, okay, then we are provably, for any level alpha that the user chooses, we can bound the expected risk in the recommendation below that level alpha, under certain, let's say, requirements of the risk function. So far so good, that's very nice, but unfortunately, we noticed that conformal risk control kind of reduces the number of available items in our item pool. Because the idea is that the more I filter items, the lower the risk will be. But in the end, it will happen that I won't have any more items to recommend to people. And therefore, we devised an additional strategy in which we, instead of removing items, we replace them with items that the user has previously seen and liked, that we deem safe. And to do that, we basically filter them beforehand by looking at their initial watch time, the first time they were seen. We did several experiments on offline experiments on this Quasho datasets, and we employing different recommendation systems and the two strategies. Okay, and well, we first noticed that on the plot on the left, we can basically perfectly control the risk, no matter the model that we use and no matter the strategy that we use. Since the empirical reduction in risk and the desired reduction in unwanted content kind of match and they align on the diagonal, and also with our approaches, which is like the one bordered in red, we can provide larger recommendation sets, okay, with more items, and with a higher NDCG. And that's because if for the standard strategy where we just remove items, in the end, for example, we can achieve 100% reduction in unwanted content. But to do so, we have to recommend basically 0 item to users, which is kind of trivial. Further, we did further experiments to understand the effects of this strategy of replacing unwanted items. And well, we first noticed on the left that depending on the model that we used, we might have to replace fewer or more items in the recommendation set. And anyway, if we want to have 100% reduction in unwanted content, just we have to basically give previously seen items. So we have no serendipity. And secondly, we also noticed that we need to choose the safe items, okay, very precisely, because if we do not do so, we might break the risk control guarantees. You can see there from like the green line that doesn't really align on the diagonal, which means that the desired reduction in unwanted content, the alpha, doesn't match actually the empirical one that you observe during the offline experiments. That was all for my side. If you have any questions, I'll be happy to answer.
So the technique is preventing me from seeing things that I have seen before and don't like. How would you extend this to show you other things like those things? Like presumably, I don't like this video of somebody being beheaded. I don't want to see other videos of people being beheaded. So is there a way to extend this technique kind of more generally on the content side?
Thank you for your question. Actually, it's very, this is something that we wanted to explore, basically different strategies to determine, let's say, potentially safe items that we want to give to a user. For example, one could say I could use maybe item created by the community, maybe videos that everybody thinks they're very nice, that they would like to be seen by most of people's. Or especially in case of like cold start issues, I think one could, for example, leverage maybe the network of your friends, or if this social network or something, to recommend items that your friends thought they were nice, so they might be nice also for you. The problem that there are really not many data to test these kind of assumptions. And in order to, let's say, obtain the control guarantees that we want, there are certain assumptions that need to be satisfied, especially when you build the conformal threshold, the lambda. And so one needs to be very, very careful when one does these things. But it's an open question. I mean, I'm open to suggestions.
Hi, thanks for the talk. My question is, you show only the reduction of unwanted content, but what is the actual performance of such model? Because typically, if you play safe, you probably wouldn't recommend something that may still be relevant. And there is some research that shows that when you reduce the number of, let's say, unwanted or low-rated items, for example, right, you also may drop the highly rated items, and then there is it's undecided threshold, like to which extent you want to do that, and there is also the difference in different model how they perform with this additional control of reducing the amount of unwanted items. So have you explored that?
So okay, just a clarification here in the plot on the right. My left. There is a drop in the NDCG, but these data are, let's say, the evaluation is done by considering the watch time, for example, here of the second time that the user has seen that video, okay, because these data are available in the dataset. So these are kind of like realistic performance, quote unquote. Surely there is a, let's say, we see a drop here, but I guess if someone was to, let's say, were to engineer better the re-ranking part, also considering the fact, for example, that this item was already previously seen, and we didn't do this. We just use like a simple model. I guess you would be able, let's say, maybe to improve that. I'm not so sure that that's the behavior you will always see, that there is like a decrease in performance. Also because in the data, we saw that, let's say, when the user sees a video a second time, the watch time seemed to be higher. Okay, so the user were to dwell more on certain videos at the second time they saw them. So this was our rationale that made sense. But as the previous question, there must be surely other strategies that one can employ rather than just using replaced item, because I agree that it might make the performances worse on the long run.